Hi, welcome back to my class in number theory. For today, we will take another algorithm for finding the greatest common divisor of two positive integers. And this algorithm is known as Blankenship's method. This Blankenship's method appeared in Mathematical Monthly in 1963. And this is another way for finding the greatest common divisor of two positive integers a and b, where a is greater than b and b is greater than 0. And this method makes use of what is known as Bisous Lemma. So we start by stating Bisous Lemma, and we will present the proof of this lemma. We read the Bisous lemma. It says for any integers a and b, there exists integers s and p such that the greatest common divisor of integers a and b is equal to s multiplied by a plus p multiplied by b. This lemma says that the greatest common divisor of any two integers a and b can be written as linear combination of the integers a and b, where s and t are also integers, elements of the set C of integers. And this expression at the right-hand side of this equation is what is known as the linear combination of the integers a and b. Bisous' theorem is an existence theorem, or Bisous lemma is an existence lemma, which means that this lemma does not give us a way of finding the greatest common divisor of the integers a and b. It also does not give us a method or a way of finding the integers s and t so that we can write the integers a and b as linear combination of them. But this lemma will be used or is used by Blankenship's method to give us an algorithm for finding the greatest common divisor of integers a and b. Now, for the proof of this lemma, we consider two cases. In the first case, we let a and b be equal to 0. And in letter b, we let a not equal to 0 and b be also a non-zero integer. We start with case 1. case 1, we let A be the zero integer, and we also let B be the zero integer. Then, the left-hand side of this equation, we will now show that the greatest common divisor of A, B, which is where A and B are both equal to 0, is equal to the linear combination of A and B, which are both equal to 0. Then, if A and B are both 0, then the left-hand side of this equation becomes the left-hand side of this equation, the greatest common divisor of A and B, becomes now the greatest common divisor of 0 and 0. And we said in the past lesson that everything divides 0, including itself. Every integer divides 0. But the set of integers has no largest element because it is an infinite set. So there is no greatest common divisor of 0 and 0. And so we define the greatest common divisor of 0 and 0 as 0. So the left-hand side, the greatest common divisor of 0 and 0 is equal to 0. Now we showed that the right-hand side of this equation is also equal to 0. And therefore we will conclude that the greatest common divisor of 0 and 0 is equal to the linear combination of A and B, where A and B are both 0. And the left-hand side now becomes the right-hand side of this equation becomes, which is SA plus TB becomes S times 0, because A is 0, plus P multiplied by B, which is 0. And as from this expression, you can see that the integers S and T can be anything, which means that they can be any integers. And regardless of what integer you take for S and for T, the sum, the product is 0. Regardless of what integer you use for T, the product T times 0 is 0. And the sum is 0. So the integers 0 and 0 can be written as a linear combination where S and T can be any integers, and the sum, the linear combination of 0 and 0 is 0. So you can see that the greatest common divisor of 0 and 0, which is 0, is equal to the linear combination of 0 and 0, which is also 0. Hence, for case 1, we conclude that the greatest common divisor of 0 and 0 is equal to the greatest common divisor of A and B is equal to the linear combination of A and B for some integers S and T, where A and B are 0. Where A and B are 0, the greatest common divisor of AB is 0, and the linear combination of A and B both equal to 0 is 0. And the linear combination of A and B, where A and B are both 0, will be 0 for any integers you substitute for S and T. We now prove the Bisous lemma for case 2, where A is not equal to 0 and B is not equal to 0. For case 2 of the proof of Bisous lemma, we consider integers A and B that are not that are both not equal to 0. And we showed that the greatest common divisor of A and B by Bisous Lemma is equal to the linear combination of A and B, where S and P are integers. And to do that, we let capital P be the set of linear combinations of all linear combinations of the integers A and B that are not both equal to 0. Again, we let capital P be the set of all linear combinations of the integers A and B. So P is the set of the linear combinations of A and B of this form MA plus NB, such that M and N are integers. Now, we will show that A minus A, B and minus B are elements of this set P, which means that A minus A, B, and minus B can be written as linear combinations. If we write the integer A as 1 times A plus 0 times B, then we can conclude that the integer A is element of the set P, because A we have written as linear combination of A and B. This expression is of this form, linear combination of A and B, where M is 1 and N is 0. Since A is a linear combination of A and B, then A, we conclude, is element of P. Similarly, minus the negative of A is also an element of P, the set of all linear combinations of A and B, if we write minus A as minus 1 multiplied by A plus 0 multiplied by B. So you can see that minus A is a linear combination of A and B. This expression is of this form, where M now is negative 1 and N is 0, the 0 integer. So minus A is a linear combination of A and B. Therefore, we conclude minus A is element of capital P, set capital P, the set of all linear combinations of the integers A and B. We can also show that B, the integer B, is an element of set P, the set of all linear combinations of A and B. If we write B as 0 multiplied by A plus 1 multiplied by B, this expression simplifies to B. But we have shown that B can be written as linear combination of A and B. And this expression is of this form, MA plus NB, where M now is 0 and N is equal to 1. Therefore, B is a linear combination of A and B for m equals 0 and n equals 1. Thus, we conclude B is an element of set P, the set of all linear combinations of A and B. And finally, we show that the negative of B is also an element of P. If we write negative b as this expression 0 multiplied by a plus negative 1 times b, which simplifies to minus b, then we can conclude that minus b is also element of p, the set of all linear combinations of the integers a and b. This is a linear combination of a and b, and this expression is of this form, ma plus nb, where m is equal to 0 and n is equal to negative 1. Because minus b is a linear combination of a and b for value of m equals 0 and for value of n equals minus 1, we conclude that minus b is element of p. Because a is not equal to 0 and b is not equal to 0, for any integer a and b, one of these, a, minus a, b, and minus b, one of these four elements of set B, must be positive. For example, if a is negative 1, then minus a is positive. If a is 2, then a is positive. If b is negative 3, then negative 3 is positive. And if b is 5, then b equals 5 is positive. I am saying that because a is not equal to 0 and b is not equal to 0, we are sure that one of these, for some values of a and b, is positive. And because these are elements of P, the set P must contain some positive integers. Again, we say that because a is not equal to 0 and b is not equal to 0, one of the elements of P, one of these four elements of P, a, minus a, b, and minus b, must be positive. And because these are elements of P and one of them must be positive, then we say that P must contain some positive integers that are linear combinations of A and B. The elements of P are linear combinations of A and B, and we have just shown that set P contains some positive integers of the form MA plus MB. Now, we will denote this set of positive integers, the set of positive elements, positive integers, elements of set P by capital Q. Again, we denote by capital Q the set of positive integers that are elements of set P. We have just shown earlier that set P contains positive integers. And we collect all these positive integers into one set and we call it set Q. So set Q is the set of all positive integers, elements of set P, and the elements of set P are of the form MA plus MB. That means that the elements of set P are linear combinations of A and B. But the elements of Q are positive, so we have this condition such that MA plus MB is greater than 0, which means that this linear combination of A and B is positive. And M and N are still integers, elements of set C. Because Q contains only the positive elements or the positive integers, elements of set P, we say that Q is a subset of P, where P is the set of all linear combinations of the integers A and B. But Q is only the set, Q contains only the positive elements of set P. And so every element of set Q is an element of set P, therefore Q is a subset of P. Then if you recall the well-ordering principle, it says that any set of positive integers has a smallest element. And because set Q here is the set of all positive integers, elements of set P, the set of linear combinations, set Q here is the set of linear combinations of A and B that are positive, greater than 0, then set Q must have a smallest element by well-ordering principle. Again, we are sure that Q, the set of positive integers, elements of set P, or the set of linear combinations of integers A and B that are positive, has a smallest positive element because of the well-ordering principle, which assures us that every set of positive integers has a smallest positive element. And it is because of this well-ordering principle that that enable us to arrange the elements of a set in order, in increasing order, because there is a smallest entry or element which we can make as our reference, and based And from that reference element, the smallest positive element, we can arrange in order the other entries of the set with positive integers as elements. So we are sure that Q has a smallest positive element, and we use D to denote the smallest positive element of Q. And because Q is the set of positive integers, linear combinations of A and B that are positive, then D here, the smallest element of Q, must be positive. That is D greater than 0. Because D is the smallest element of Q, then D must be element of Q. And it is the smallest element of Q. Because this element of Q, D must be positive, greater than 0. Because the elements of Q are positive integers of the form MA plus MB, or linear combinations of A and B. And because this element of Q, it can be written as a linear combination of A and B. And we write D equals the linear combination of A and B for some integers S and T, element of C. We now let E, small letter E, as the greatest common divisor of the integers A and B. And we will show here that E is equal to D. And if we can show that, we can conclude that the greatest common divisor of AB is equal to the linear combination of A and B. And by definition of common divisor, E is the greatest common divisor of A and B, which means that it is a common divisor of A and B, which means that E divides A and E divides B. By definition of common divisor or greatest common divisor, if E is the greatest common divisor of the integers A and B, this implies that E divides A, exactly divides the integer A, and E also divides exactly the integer B. That is, the remainder is 0 when you divide A by E, and also the remainder is 0 when you divide B by E. Now, if you recall in one of the properties of divisibility, the linearity property says that if E divides A and E divides B, then E must also divide the linear combination of A and B. Again, by linearity property, if E divides A and E divides B, this implies that E must also divide the linear combination of A and B. And we write the linear combination of A and B as SA plus TB for some integers S and T elements sub C. But this linear combination of SA and TD is equal to D, where D we take as the smallest positive element of set Q. And we write, because D is an element of Q, it is a linear combination of A and B of this form. In particular, we take M equals S and N equals T. So D is equal to SA plus TB, and this now becomes E divides D. Thus, we conclude that E divides D. Next, we will show that D divides E. And if we can show that E divides D and D divides E, then E must be equal to D. Far we have shown that E, which we let as the greatest common divisor of A and B, divides D. And earlier we take D as the smallest element of Q. Therefore, we say D is a positive integer because Q is the set of all positive integers, elements of set P, whose elements are linear combinations of A and B. And because E is the greatest common divisor of A and B, and we know that the greatest common divisor of any two integers is a positive integer. Therefore, E here, if E is the greatest common divisor of integers A and B, then E must be positive, greater than 0. And we know that D is greater than 0 because D is element of set Q. And we have shown that E divides D. And using these three information, we apply another property of divisibility. Another properties, one of the properties of divisibility is the comparison property. The comparison property says that if E is greater than 0 and D is greater than 0 and E divides D, then E must be less than equal to D. Again, because E is greater than 0 and D is greater than 0, and we have shown that E divides D, D is equal to the linear combination of A and B of the form SA plus TB for some integers S and T, then by comparison property of divisibility, we conclude that E is less than equal to D. Now, E here is greater than 0. So, E here must be also an element of set Q. But we already know that D is the smallest element of set Q. Hence, if E is element of set Q and D is the smallest element of set Q, E here cannot be less than D. Therefore, we conclude that E must be equal to D. And to show that E is really equal to D, we know earlier that E is the greatest common divisor of A and B. E divides A and E divides B. And if E is equal to D, we must show that D also divides A and D also divides B. In that case, E must be equal to D. We now show that D divides A and D divides B. If we can show that these are true, and then we will conclude that E is equal to D and not less than D, because E is positive, it is an element of Q, and D is already the smallest element of set P, so E cannot be less than D, and we will show that E is equal to D. And earlier we know that E divides A and E divides B, and for E to be equal to D, we must show that D divides A and D divides B. And we apply the division algorithm to write A as D multiplied by Q1 plus R1, where the remainder R1 is greater than equal to 0, but less than D. From this equation, we solve for R1 by transposing dq to the left-hand side. We have R1 is equal to A, transpose dq1 to the left-hand side, we get minus dq1. But earlier, we let D as, because D is a linear combination, because D is an element of set P, it is a linear combination of the integers A and B. And earlier, we write D as equal to SA plus TB. So we replace in this equation D with SA plus TB. We have R1 is equal to A minus B. B is linear combination of A and B, SA plus TB, multiplied by Q1. Now we remove the grouping symbol and we collect the like terms. Multiply each of these terms by negative Q1. We have A negative Q1 multiplied by SA, you get minus SA Q1. And negative Q1 multiplied by TB, you get minus TB Q1. In the first two terms, common factor is A, and we factor A. The other factor here is obtained by dividing these two terms by A. We have A divided by A is 1 minus SAQ1 divided by A, you get SQ1. And we write this as plus minus TQ1 multiplied by B. Now you can see that R1 is a linear combination of A and B, where the integers m is equal to 1 minus SQ1 and n is negative TQ1. But we know that R1 is greater than 0. Again, R1 is greater than 0, and R1 we have shown is a linear combination of A and B. And that means that R1 is an element of set Q. the set of all positive integers elements of set P that are linear combinations of A and B. Again, because R1 is greater than 0 and R1 we have shown is a linear combination of A and B, we conclude that R1 is an element of Q. But we will show that this is not possible because we also have this condition that R1 is less than D. If R1 is less than D and this condition must be satisfied, R1 must be less than D, and D is already the smallest element of set Q, then R1 must not be an element of Q. Again, because there is this condition from division algorithm that R1, the remainder R1 must be less than D, and if D is already the smallest element of Q and R1 is less than D, then R1 must not be an element of Q. So this should not be true. R1 element of Q. And because R1 is not an element of set Q, then R1 is not greater than 0 because the elements of Q are positive integers that are elements of set P whose elements are linear combinations of A and B. And because R1 is not equal to 0, is not greater than 0, thus we conclude that R1 must be 0. We have shown here that R1 is not an element of Q, and Q is the set of positive integers. If R1 is not an element of Q, then this must not also be true. R1 is not greater than 0. And if R1 is not an element of Q, it is not positive, but it is less than D, and D is already the smallest element of set Q, and the smallest positive integer is 1, then R1 must be 0. If R1 is 0, then this becomes A equals BQ. Again, R1 must be 0, and this equation simplifies to A equals BQ1. R1 is 0. And A equals BQ1, by definition of divisibility, D must divide A. By definition of divisibility, if D divides A, then A is equal to D times some integer element of set C. In this case, the integer is Q1. Thus, we have shown that D divides A. Next, we will show that D also divides B. Earlier, we know that E divides A and E divides B. Now, we have shown that D divides A, and what is left now to show that E is equal to D is to show that D also divides B. To show that D divides P, we again apply the division algorithm by writing D as dq plus R2, where Q2 and R2 are integers, and R2 must satisfy this inequality R2 must be greater than equal to 0, but less than D. Again, we solve for R2 from this equation by transposing dq2 to the left-hand side. R2 now is equal to B. Transpose dq2 to the left-hand side, you get B minus dq2. And earlier we let D as the smallest element of Q, and the elements of Q are linear combinations of A and B, and we let D equals the linear combinations of A and B for some integers S and T, and we let D equals SA plus TB. In this equation, we now replace D with SA plus TB. And we remove the grouping symbols here by distributive property of multiplication over addition. Multiply each of these terms by negative Q2. We have B minus SAQ2 negative Q2 multiplied by TB minus TBQ2. And we collect the first and last terms because they have common factor B. R2 now is equal to the first term B minus the last term TBQ. TBQ2. And we write minus SAQ2 as plus minus SQ2 multiplied by A. What we want to show here is that R is a linear combination of the integers A and B. And we write this first as the first term. And from this group, we factor B. If you factor B, the other factor is obtained by dividing this binomial by B. B divided by B is 1. Minus TBQ2 divided by B is minus TQ2. What we have shown here is that R2 is a linear combination of the integers A and B. And because R2 is a linear combination of A and B, it must be an element of set capital P, the set of all linear combinations of A and B. But we have this condition that must be satisfied. R2 is greater than 0. If R2 is greater than 0 and R2 is a linear combination of integers A and B, then R2 is an element of Q, the set of positive integers that are linear combinations of A and B. Again, we will show that this is not possible because this condition R2 less than D must also be satisfied. And if R2 is less than D, since the condition R2 less than D must be satisfied, and we know that D is already the smallest positive integer element of set Q, then we can conclude that R2 is not an element of Q. If R2 is less than D and D is already the smallest element of Q, then R2 is not an element of Q, which we have shown that these two are not true. If R2 is not an element of Q, Q is the set of positive integers that are linear combinations of A and B, then R2 is not greater than 0. And what is the only value of R2 that is left? R2 is not greater than 0. Then the only value of R2 is 0. That is, R2 must be 0. And if R2 is equal to 0, replace R2 with 0. This equation simplifies to B equals BQ2. Now, B equals BQ, it means or it implies that D divides B. Because by definition of divisibility, if B divides B, then B must be written as D times some integer Q sub 2. So we have shown now that D divides B. Now we collect all the results. Because E is the greatest common divisor of A and B, then by definition of common divisor, E must divide A and E must divide B. And in the previous two results, the last two results, we have shown that B divides A and B divides B. And by comparison property earlier, we have shown that if E greater than 0 and B greater than 0 and E divides D, then we conclude that E is less than equal to D. But D is already the smallest element of Q, so E here cannot be less than D. And we are left with the only condition that must hold, that is E must be equal to D. And because E is equal to D, we therefore conclude that E is the greatest common divisor of A and B, equals B, and earlier we write B as the linear combination of A and B of the form SA plus PP. And this completes the proof of Bisous' lemma that says for any integers A and B, there exist integers S and T such that the greatest common divisor of A and B can be written as linear combination of A and B for some integers S and T elements of Z. Again, Bisous' lemma is an existence lemma, which means that it does not give us a procedure for finding the greatest common divisor of A and B. But this lemma was used by Blankenship to develop an algorithm for finding the greatest common divisor of A and B, as well as the integers S and T. And this method is called Blankenship's method. We now take some examples for applying the Blankenship's method to find the greatest common divisor of two integers. And that's the completion of our lesson for today, Bisous' lemma. And again, this lemma is just an existence theorem. An existence lemma, it does not provide us with a method for finding the greatest common divisors of two integers A and B, as well as the integers M and N that we use to write A and B as linear combinations. But we will use Bisous' lemma as a check when we apply Blankenship's method, the algorithm for finding the greatest common divisor of two integers A and B, where A is greater than B and B is greater than 0. Both integers are positive, A and B are both positive, but A is greater than B. If you have a question about the lesson today, please ask your question in the comments below. Thank you for joining me in my class today in number theory.